Okay, guys, so this is me recording me. That's a problem. Okay, so this was a video I did earlier, but now I have lost my mouse. Let's turn that off. That's just weird. Okay, so there's Beaker. So we're looking at electrolysis of solutions, so not molten salts. We have a 1 molar strontium fluoride solution here, and you can see the way the battery is hooked up. So you should be able to determine what the anode and cathode are. So if you want to take a second and try to do that, and also like electron flow, and maybe what should be reduced and should be oxidized. So strontium ions in solution. And also some fluoride ions. Now remember, the word molar means dissolved in water, right? But here we go. So let's put strontium ions. They're very low down on the left-hand side of the table at negative 2.89. And the fluoride ions are relatively high. In fact, they're the highest thing up on the table at positive 2.87. Okay, so you can see definitely strontium and fluoride are two different things that can be reduced and oxidized, and they are step up, which would indicate a non-spontaneous reaction. Remember, the solution, well, it's a solution, right? So besides the strontium ions and the fluoride ions, we also have to consider where water is. So let's see if you can find that on your table. So there's our water in the beaker. So we have a third chemical we have to worry about. And under the reduction column, or the oxidizing agents, we find water at negative 0.41. And that's the reduction of water. And then the oxidation of water also appears on the right-hand side of the table at positive 0.8. So we have two things to consider now about possible things that get reduced and possible things that get oxidized. So we need to remember the rule on that, how we determine that. So looking at the table, you can see these arrows on both the left-hand side and the right-hand side, indicating the strength of the oxidizing agents and reducing agents. So on the left-hand side, the thing highest up is the strongest oxidizing agent, or the most likely thing to get reduced, which would be water. So water would beat strontium here. And then on the right-hand side, we have the thing lowest down, which in this case is lowest on that side, would be the water again. So here we have water higher up on the left side and lower down on the right side. So it actually is both the strongest reducing agent and strongest oxidizing agent of the chemicals that are there. So the water will actually go to both electrodes, kind of like the tin did in the reaction above. And at one of the electrodes, you're going to have oxidation and reduction. So we might ask you what forms at the carbon electrode and what forms at the platinum electrode. So you'd have to know which one's the anode and which one's the cathode. So determining electron flow, we know it flows out the negative end. So we should be flowing from the platinum electrode to the carbon electrode, which makes the carbon the cathode. It makes the platinum the anode in this case. So water is going to be reduced, and in that case, it turns into hydrogen gas and also produces hydroxide ions. So that would alter the pH of the solution. So we see bubbles forming around the carbon electrode, and those would be bubbles of hydrogen gas. Okay, and then at the anode, we have the oxidation of water, which will produce O2, and will also produce hydrogen ions at the platinum electrode. So we actually would get bubbles forming around both electrodes, but the gases would be different gases. So we'd have oxygen gas and hydrogen gas. And you might want to collect those in an experiment. Maybe there's a reason for doing this thing. You could use the hydrogen as a fuel source. And of course, you could use the oxygen as breathable gas. So in space exploration, this might be a practical reaction to do. And you notice that the strontium and fluoride, neither of those ions actually reacted here. So they were almost acting as spectator ions in the situation. But also notice that the reduction of water produces hydroxides, which would make things more basic. So you're getting these hydroxides being produced. So the pH would be going up around that electrode. And then at the anode, you're also getting hydrogen ions being produced. So you're actually making the pH go down. And what you would notice is that for every 2 OH you make 2 H plus. So the effect of this would be an overall neutral result for the reaction. And this means that although the pH is changing at each terminal, the overall pH of the solution would remain constant. It would be pH 7. And I think Beaker likes that a lot. And then if you want to calculate the E naught of the cell, you have to remember which reaction you're going to flip the sign on. So always the oxidation reaction gets flipped, because these are reduction potentials. If you look at the top of the table, it's a standard reduction potential. So the water's reduction potential is negative 0.41, and the reaction would remain at negative 0.41. However, the other reaction, we need to change that to negative 0.82. So Beaker caught that for us. And now that would be the oxidation potential for water being oxidized. And then we add these numbers together. That should give us negative 1.23 volts. Now that means that this particular reaction is non-spontaneous and would require a battery to have 1.23 volts of electricity. Okay. So our battery would have to have 1.23 or more, I guess, volts. If it was a 5 volt battery, that would be good. If it was a 1 volt battery, that would not work for us here. Okay, so I'm gonna move on to the other cell here, and I think the video actually has okay volume at this point. So I'm going to stop recording here. But this is our last example we're gonna do.